All right, so I just want to go over two problems in the homework, particularly 1 and 4. I think some people maybe had some confusion on those problems. Um, so first of all, remember the kind of starting point for problem 1 is that we have a semi-normed vector space, and we define x tilde to be the set of all these classes generated by stuff in big X under this equivalence relation where X is equivalent to Y if the norm of X minus Y equals 0. So big X is a semi-normed vector space, so X minus Y norm equals 0 does not necessarily imply X equals Y. All right, right, so we want to give X tilde an addition structure, a vector space structure. So if A equals the class generated by X, well, let's just start off, forget about that. Let's just say let's say A and B are something in X tilde. So let's say A is the class generated by X and B is the class generated by Y. So I'm stating a definition. We're defining A plus B to be the class generated by X plus Y. Big X is certainly a vector space, so this is certainly an X tilde. Okay. Now let's suppose that X is equivalent to X prime and Y is equivalent to Y prime, which is the exact same thing as saying that these classes, class generated by X and X prime are the same, and the class generated by Y and Y prime are the same. So by definition, A plus B, we said, was this right here. Because, well, this is what A is, and this is what B is. Scoot this over here a bit, but so A is a class generated by X prime, B is a class generated by Y prime. So by definition, A plus B is this class here, the class generated by X prime and Y prime. So we have a potential problem here. Very simply, if these two classes are not the same, then we have two different definitions of A plus B. Okay. But that's, the homework was prove that they are the same. Okay. And I'll go very quickly. Most people did this correctly. So how do you prove that these two are the same? Now, if they are the same, we have no problem. we have two seemingly different definitions, but they turn out to be the same. So yeah, if we do have equality, all is well. So it's the same situation in algebra when you talk about quotient groups, quotient rings. You know, you always have to check. And if you define, if you have something defined in terms of a representative of your class, you always have to prove that it's well defined. It's independent of which representative you pick. This is no different. So I probably should have been clearer in the video before. So let's prove that these two are the same, which is the same thing as saying x plus y is equivalent to x prime plus y prime. And there's, yeah, everyone basically got this right. So I was happy about that. What are we proving? X plus y is equivalent to x prime plus y prime. Sorry about that. So by definition, we need to check that the norm of this is 0, which is pretty easy. This is just x minus x prime, y minus y prime. Well, that's equal to 0 plus 0 is 0. So this norm here is 0. So that implies x plus y is equivalent to x prime plus y prime, which is the same thing, again, as saying these two classes are the same. So the punchline that I'm really trying to emphasize is that, let me kind of redo this here a little bit, kind of make it intentionally a little more muddled, I guess. So in other words, by definition, we're saying as these, class generated by x plus the class generated by y is class generated by x plus y. You can't prove this. It's a definition. You can't prove something that you're defining. So like you just, what I'm circling, you cannot prove because it's how I'm defining. This by itself, this plus here is meaningless because I haven't defined it yet. So yeah, so hopefully that made a little clarified things a bit. And also for problem 4, try to go through that a little quickly. Okay, so problem 4, remember C0 is, well, not going to write down exactly what problem 4 is, but so let's say we have a sequence of stuff in C0. And let's say it is Cauchy. Okay, so what does that mean? For any epsilon bigger than 0, there exists an n, depending on epsilon, where this supremum here so I'll use superscript as before to denote each individual element in C0. Well, each xn is itself a sequence, so subscript is for that sequence element. Sorry, nm bigger than n implies that, well, this is by definition the norm, xn minus xm. That's less than epsilon. Okay. So yeah, so for fixed J0, that means fairly trivially, well, certainly less than or equal to the sup for any fixed J0. And this is true. And yeah, just to emphasize, this only depends on epsilon. So in other words, for fixed J0, so for fixed J0, sorry about that. This is Cauchy. So it converges. So let's say xj0 is this limit here. Okay, so we have a few things to prove. We have to prove, well, first of all, if x is x1, x2, et cetera, we got to prove that x is in C0. And we also have to prove that we do have convergence in the C0 norm. Neither of them are particularly hard, but we do have to prove that. So let's do B first. Okay, so the proof of B is as follows. Let's pick epsilon bigger than 0. Right, so you got to be a little careful here. So fix J0, natural number J0. And fix some m greater than big N coming from here. Where this here is less than epsilon. For fixed J0, xj0m converges xj0 by definition, so we can always do this. Now, the thing you need to be a little careful about is, well, for each J0, we have this limit. We don't have any uniformity whatsoever. We're basically in B trying to prove uniform convergence, but we really have no uniformity, sorry about that, in J0. So what we need to do is be mindful that this might depend on, well, certainly depends on epsilon, it might depend on J0, but that's okay. That doesn't matter. N bigger than big N, which only depends on epsilon, implies that xj0, and remember J0 is arbitrary, it's just some arbitrary fixed natural number. So we're just going to use this really just to get what we want and really, yeah, it's just like an intermediary helper in some sense. Well, M and N are both bigger than big N, so certainly this is less than epsilon. Well, M is bigger than big N, so this is less than epsilon. So this is less than or equal to 2, or really less than, whatever, less than 2 epsilon. Okay, so that J0 is arbitrary. So the supremum over all J0 is less than 2 epsilon. So by definition, this implies that the sup is less than 2 epsilon. So that's less than 2 epsilon. And so that proves B. So let's quickly prove A. All right, and it's a kind of similar logic. So fix n just depending on epsilon, where x minus xn is less than epsilon. Again, let's start off with some epsilon. Okay. Well, we know that this here is in C0. So again, this is not too hard, but you do want to be a little careful. You just don't want to just throw out limits and, kind of willy-nilly. You want to be a little quantitative here and a little careful. Right, sorry about that. So because xn is in C0, we know that this number here equals 0. So because of this, we can pick, let's say, I don't know, pick capital J. Well, so this really depends on, sorry, that doesn't make sense. That makes more sense here. Well, J bigger than, little j bigger than big J implies that xn j is less than epsilon. So let's be a little careful. This depends on n and epsilon. Well, that's a bit silly because n depends on epsilon. So this really just depends on epsilon. Because again, little n just depends on epsilon. So it's just, yeah, it just depends on epsilon. Okay, I mean, I guess epsilon over 2, but whatever, it doesn't matter. So let's finish this up. Where it went, but that's okay. Sorry about that. Okay, so what does that mean? That means, well, if J is bigger, little j is bigger than big J, then xj is less than or equal to xj minus xjn plus xjn. Well, again, this is certainly less than or equal to the supa over all j of these absolute values. So that's the norm. Well, j is bigger than big J, so this is less than epsilon. So that's 2 epsilon. So we found a big J depending on epsilon, where little j is bigger than big J implies absolute value of xj is less than 2 epsilon. So that implies that x is in C0. So sorry if this was a little rushed. I have a seminar in a few minutes. So, yeah, so, right. So hopefully this clarified, what I really kind of wanted to see for problem 4. All right, so long, take care. Hopefully I see you in the seminar. If not, that's okay. No worries. All right, bye-bye.